interested in and are keen to know the progress, co-utilization of coal and biomass experiences in Europe by Professor Klaus R.G. Haynes, Professor Emeritus, University of Stuttgart, Germany. Dr. Klaus R.G. Haynes is an alumnus of the Technical University Aachen, Germany, and the famed Imperial College London, and he has won several awards for outstanding scientific and technological achievements in Europe, China, and the USA. His illustrious professional career spanning over 4.5 decades, he has taken up many responsibilities as research engineer at the International Flame Research Foundation, Netherlands, and then head of R&D at the German utility RWE. In parallel, he also took to academics as the chair of the energy technology at the University of Delft, and since 1992 he has taken up very challenging positions at the University of Stuttgart, Germany, before retiring in 2004. After that, he was retained as the acting director of the Institute of Combustion Technology until 2008. Professor Haynes was appointed Fellow of the Brown Coal Initiative, Australia, and is in charge of BCIA-funded projects for improvement and utilization of low-rank coals such as brown coals and lignite since November 2010. So I hand over the floor to Dr. Haynes.
Thank you very much for the nice introductions. Sometimes nice to remember what you already knew in lifetime. With this, let me start straight away here in presentation. In my presentation, let's see where you can find it here. In the program, you've seen that all, and let's talk about the biomass. Actually, we talk a little bit about the background of biomass. And what you see here, so the historic background, most of you will know, is a feedstock for human existence, direct use as food tools and clothes, and indirect use, obviously, as heat source. Now, in the industrial age, about 150 years ago, the conversion to power and chemicals started and is still going on in some of the countries. Now, early in the last century, the generation of transport fuels, particularly in Europe, in Central Europe, was important. And here you see one of the historic photos of a wood gasifier used in Germany here in around about the 50s for pyrolysis gas for running a car. In the times after that, consecutive to this technology, the biomass was replaced by coal because that was more efficient, or by gas, using town gas for easier to use in household and small-scale industry. And then later on, as we all know, natural gas came into power, and so because that was much cheaper and biomass was lost the interest. However, we have in Europe, we had found in the 80s and 90s a renewed interest in for various reasons. We had locally and regionally biomasses available, biomasses and wastes. We used also residues from agriculture and forestry, waste from domestic community industrial process was available, and you could, in using these fuels, these biogenic fuels, could reduce or preserve fossil fuels, as you can see here, and also you could reduce the biomass, the reduction of the dependence on fuel imports, as well as we had several areas in Europe where we had surplus farming areas, and we could use those farming areas by growing biomass. Next one. That's one back. Okay. All right. But still, how to continue here?
Yes, don't go.
Continue. Oh, the center one. Okay. Sorry. No. Oh, yes. Okay. Yeah. So, in the 90s and beyond, we had in Europe new drivers, as you can see here. First of all, worldwide, the global climate issue, and that the greenhouse gas concern was important. Then we talked about the sustainability of energy supply. So we expected on those days a strong increase in energy and electricity demand, and that with limiting access to primary energy resources. And then we had the resulting worldwide actions, and particularly also in Europe, the Kyoto Protocol, 1997. Everybody is informed about that one, I guess. And in Europe, we changed the policy slightly, and our political commitments towards sustainable energy supply and environment protection at competitive level was the key issue of our research and development in industry and in research. Again. No, this is good here. That's true. Let's see this one. Okay, right. Let's try this one. So this one is obviously slightly different from my computer. So what happens in Europe? What's the energy policy in the European Commission? Was, as we heard in other papers already, limiting to global, try to limit the global climate change to 2 degrees C, and what was the strategic objective? At least 20% reduction of greenhouse gases by 2020, 50% probably 50% by 2050, and that compared to the 1990 standards. And how to do that in terms of transport, buildings, and electricity and heat generation. And tomorrow in the afternoon, in the much longer presentation, I will come to more details. So, how to do that? Energy sources, a mix of all primary energy options, which we had, including nuclear, 1/3 in electricity, and 15% of the total mix. Those were the political incentives. And talking about renewables, 20% by 2020, and on this 20%, 10% in biofuels for electric generation, heating, cooling, and transport. Now, the consequences for the heat and power generation in Europe were quite a few ones, as you can see here. The European Union or Commission initiated research into the substitution of high carbon coals by lower carbon biomass, and everybody talked on those days, and worldwide it still does, the carbon neutral, so-called carbon neutral resources. And this in Europe through multi-partner, multi-country projects in partnership between industry, small, medium enterprises, and academia, so all the partners were involved. And this including laboratory, pilot, and industrial scale, and finally was financially supported by the European Commission. So this large cluster research became modern in the around about 1990, 1993, and you see that here the first one where the specific specific co-utilization research in Europe, 1993 to 94, the so-called APAS project. And we had on the right side, you see on the bottom here, the co-gasification, 18 partners in Europe from 8 different European countries, and in co-combustion, 25 partners in 8 countries. And again, I will come to some more details, research details tomorrow in a much longer session in the afternoon. So, what kind of biogenic fuels did we discuss and research in Europe? Untreated biomass, obviously one group, then the cultivated biomass, and we also had residues from agriculture industry and residues from industrial processes, as you see here, the four groups. And if we talk about untreated biomass, that's obviously the most important ones: the forest residues, bark, sawdust, straw, a very important part in Europe, particularly in Scandinavian countries. I will give you later on an example of this one. And even roadside grass from motorways was mowed, dried, and used as a biofuel, co-combustion molding with some of the industrial boilers. Cultivated biomass, obviously, short rotation forestry, cereals, rape, and then you see here a selection of the residues, and I'm not going into the details because, again, some of the results will be given tomorrow. Please understand that this one is here only an introduction, more or less. Here we are. So now, to give you an idea between the hard coals, brown coals, and typical wood and straw biomasses, including some RDF, refuse-derived fuels, and some dried sewage sludge, another important biogenic fuels used in Europe. And you see here what is important. First of all, you see the two biomass examples here, wood and straw, a much different LCV heating value due to the different moisture content compared to the bituminous coal, 5% moisture here, whilst we have lignite and brown coals here, 50% in Europe. But the wood and straws have much higher water contents and therefore lower heating values than the bituminous coal. Another important thing is that I would like to mention here is the ash. The ashes are much lower normally in wood or other biomasses compared to the fuels, to normal fossil fuels. And what I'm looking here, the volatile. You see, the volatiles are much more important in terms of ignition and combustion, and I think that is one of the advantages which you can use in these fuels. So, how do we do that? Well, certainly simultaneous feed of biogenic fuels and solid fuels, co-combustion mode. I will show you in a few examples in a moment. Why do we do that? Obviously, reducing greenhouse gases for political and strategic reasons, and you can apply that in heat and electricity generation. That is mostly done in Europe, or you can use it as a combustion or the gasification, gas production for fuels and chemical feedstock, and obviously also for heat and electricity generation. So what are the benefits? Obviously, the first line, we have a partial replacement of high carbon fuels by low carbon fuels. You have advantages you can use those biomasses in addition to a coal, for example, in large scale systems, and that helps you to run biomass under high efficiencies and low emissions of the larger boiler system. Next slide is not so important. We have, if you have low biomass percentages in the order of 5 to 10%, you have actually no real boiler operation problems in terms of fouling, spreading, or corrosion. I come to that later on another example. There is no continuous biomass supply as long as you use only smaller percentages. I mentioned already the high volatile biomass, high volatility of the biomass can be used. It is advantageous in ignition and combustion. The capital costs are advantageous in co-combustion in comparison to mono-combustion, mono-use. And I'll give you an example in a moment, and you can compensate the fluctuating availability of renewable get this wrong here in renewable sources. We have two different technology approaches here. That is a direct feed to the same reactor, the reactor, or the indirect one. So we have a separate fuel conversion feed for coal and biomass. And just to give you an example here, or two examples, here on the right-hand side you have the indirect use, and on the left-hand side you have the direct use. Let's start with the left-hand side. You can see here the biomass can be fed either number one, directly to the coal processing plant or the coal milling plant, or the number two is added to the coal prior to the burners, or have a separate burner, that's number three, separate burner for the waste or biomass feed. That's the direct use. The indirect use on the right-hand side is mostly done in a sort of fluidized bed reactor where you gasify or you pyrolyze your biogenic fuel, and then you can use this gas either as a product gas directly as additional fuel. You can use it as an overfire in an overfire system, or directly in the burners. This we can, for time reasons, probably stop that. No, okay. This is important. You have on top, you have the pulverized fuel situation, where the experience in Europe is roughly 0 to 15% biomass as maximum to be fed to a large boiler, or in CFB. We heard that from John a few moments ago. CFB systems of fluidized bed in general can run different biomasses, even up to 100% compared to coal. So the indirect use, I said the three possibilities. The top one is, for example, biomass pyrolysis, where you have a char, and this char you can use as additional fuel in your boiler, and the gas from pyrolysis is also a gaseous additional fuel. I'll give you later on one example. The second, the middle one here, if you go down here, there's a biomass proper gasifier, either by oxygen or by steam, and you have a gas cleaning and use this as additional fuel in a coal-fired boiler. And the third one is obviously here the lower one, where you have a biomass washing, so for example, reduce the nitrogen content, the sodium content, and you can use that as additional fuel. So all these three possibilities are available in industry. Comparison of investment costs at about 2000, when this research was very high in Europe. You see therefore here it's in German marks given per kilowatt electrical. That was before the euro, but we had on those days a lot of plants operating. For example, the red ones here is the biomass only plants, where small-scale boilers were using at three different locations here. Below there's the names of the locations. Used only biomass, and you see here the investment costs, and that compared to the blue ones. Those are boilers where in the first one is the Dutch one, the second one is the Danish one, the Irish one, then an Austrian one, and then a summary of straw plants or wood plants. And you see that the costs, the investment costs to use in addition of biomass to a boiler are much less than a pure a plant dedicated only to biomass. So we can leave this now. Some examples here, for example, in Denmark, they used in medium-sized boilers straw, and the technology on those days was that you produce bales. You harvest the straw in roughly 40, as an example, 4 tons straw per hectare. And you press special machines here, bales or 500 kilo bales, and to transport those with special trucks to the power plant. And in order to be economically interesting, the transport shouldn't be, or was on those days calculated not to be further than 30 kilometers from the power plant in order to be economically viable. So this straw was then coming into the power plant. You see here the storage and automatic transportation. On the lower draft, the lower little drawing here, you see the transport conveyor here for the bales. Then you have a shredder machine, followed by a transportation system, in particular for sieving more or less any kinds of sand and contaminants from the straw. And this one then was further transported pneumatically toward the actual boiler. And you see here one of the typical combined straw and coal burners from those days. And you have the straw in the center, primarily fed. You have an oil, obviously an oil burner here for ignition. You have the coal in the annulus, and around the straw, and the air everywhere as secondary air, as usual. There is another possibility which was in detail investigated. There's a co-combustion of SCRs, so solid refined fuels. So that means from garbage and industrial waste, by treating those in terms of milling or sizing, separation, to have a higher degree of biomass in this final blend. And this was used here in this Weisweiler power plant, the lignite power plant in Germany. And this fuel, which was in addition fed to the lignite, the normal lignite fed power plant, was paper sludge, and these are SCR. It was the boil efficiency with this combination of about up to 3 and 5% of the additional paper sludge and SRF came up to close to 90%. Here's the steam data. You see it's one of the older 600 megawatt units at subcritical pressure. And here is a scheme how this was done. The fuel was transported via a bunker in this the yellow part here on the left bottom. Then we have a transport conveyor here into a bunker, a separate bunker, fed into the coal mine, in the coal mains here. That is the lower part. Both milled together and then transported and burned in the boiler. Tomorrow I will give you some more details about this one. Another one was the same types of fuel as well as the sewage gas used in co-combustion mode in CFBs, two CFBs with 235 megawatts thermal each capacity. And you see here the scheme. You have on top the siren, top left, the pre-dried sewage sludge transported and fed into below the downcomer here into this fluidized bed, and the same applies here to the SRF fuel in a separate bunker system, also fed into the fluidized bed, the lower part, and the main fuel obviously is the run-of-mine lignite with about 90 up to 95% of the total and the 5% with the additional biomasses. Another example is then the Avadora plant in Denmark, where we have two separate boilers. So we don't feed the biomass in the same boiler. This is the center one here, the main boiler, a large unit was originally produced or built for coal, later on changed into natural gas and oil, including in the years after that some wood pellets, and in the parallel boiler we had the straw boiler. And you see both fed, they are steam, they produce steam into a steam turbine for electricity on one side and district heating on the other side. So a large Danish plant. In the photos you see an aerial view of the total plant, and the lower one you see here, the big vessel is the biomass vessel for the straw. Also this plant has a natural gas turbine in parallel. You see all the various use that the various different fuels could have used in this Danish plant. The only indigenous fuel in Denmark is straw. In this case, everything else has to be imported. So therefore, it is understandable that we tried all the ways of fuels available. So then let's talk about the gasification, the co-gasification. So historically, obviously, we know that the thermal decomposition of solid fuels, the wood and later coal, was used for lighting, heating, and cooking. More recently than by steam and air, oxygen supported gasification for power generation or for motors and turbines. And we also had the combination with additional gas conversion processes for the production of liquid fuels which we stock for chemical plants. So, why biomass gasification? Obviously, you see here the part utilization of biogenic fuels in large-scale power generation. Some examples will come. And as I said earlier, if you have this gasification in a separate unit, there are no restriction on the main boiler operation and on the main boiler operation as well as the availability by the biomass system. And this is important. We heard that from John Ash. The utilization of gas is very important. If you have two different systems for biomass and for the main fuel, there are no quality change of the main boiler ash, which you normally use in cement or the industry or somewhere else. So that photo we saw already, this sketch we saw already. Leave that. As I said, in Europe, either the bubbling fluidized bed on the right and the left, or the circulating fluidized bed on the right, as a sketch, are used both for the pre-gasification or pyrolysis of biomasses. And here some a plant in Austria, the Güssing plant, where you have a the pointer's nice, but it should really work. So you have a gasifier here, and followed by a combustion section. So the gasifier to the top, you see here, you can produce the gas, clean the gas, and use it after scrubbing as a clean gas for different purposes. Or you can burn the gas here directly in the combustion section and use the flue gas, and to get rid of the flue gases via the gas cooler and so very straightforward technology, but that was one of the first biomass plants, biomass gasification plants in Europe, research in this century. Another very important example is this one, because this one partly financed by the European Union, and you see here you have a gas, and that is in Finland. The Lahti plant is in Finland, a fairly sizable plant, 350 megawatts. You have a biomass on top here on the left side. We have the biomass feed and storage, and then you feed the gasifier, which is below there, a 50 megawatt gasifier, and the gas which is produced is underfed actually through a separate burner that used to be the case in this, on those days, coal-fired system. Another one in the Netherlands is the Armer power plant, which is here. Unfortunately, in this graph it doesn't show really. You can't hardly read it, but anyway, the lower, I'll show you on this side here. That is the biomass storage system here, transport and the storage system, and then fed here to, in this case, wood chips, fed later on here directly to a gasifier, circular fluidized bed gasifier system, and the gas is then used. It's cleaned here, you have a cleaning system here, and directly used in the large boiler. The total capacity of biofuel is roughly 3%. We do have some problems in biomass utilization, shortcomings. Obviously, if you have a restricted seasonal availability, depends what kind of biomass you would use, straw, wood, or whatever. So the mass or the quality and the variability is pretty much. And as you biomass is not a homogeneous mass. Biomass is such a variety of different analysis and origin. And so therefore, the experience is you have to adjust your system to a particular biomass or a group of biomasses, otherwise you get into trouble. And I will give you some of the ideas about the trouble in a moment. The low energy density requires large masses in terms of replacing fossil fuels. And so therefore you need high output specific requirements. We do have, for many fuels, a high fuel cost, first of all, in particular if you have to import them, like pellets from Canada, as we heard earlier, and many of the Danish plants or Scandinavian plants do use imported biomasses. And the preparation costs could be quite enormous, particularly if you have fibrous material like rice straw or normal straw. Grain material, and you may have potential problems during operation, and some of these problems are given here in this little graph. You see the list here donated. The number one, or the numbers give you the areas in the boiler system or the whole power plant system where such problems can occur. So number one is in the middle, and depends on the capacity. If you have low capacity biomass added directly to the mill, this is not a problem, but if you run into higher percentages of biomass, you have to watch it. Number two is in the combustion chamber, slagging and fouling. I'll give you a nice photo later on here. And it applies to the slagging fouling at the walls of the superheater, of the whole combustion chamber inside, and then to the particular superheater areas where you have fouling and probably also corrosion. Depends on the biomass. If you have a high chloride biomass, you have to be careful. Number four is the convective heat exchanges, again fouling and erosion. So that's number three and number four. It's identical, depends on the temperature range, of course. Then we have number five, in case you have a DNOx system, and all the European systems nowadays have DNOx systems. It's different from your country as far as I know. So the catalysts, the SCR catalysts, experience some deactivation and some erosion, depends on what kind of biomass you have. And then you have further downstream in the flue gas cleaning system, the ESP, we have dust accumulations, and the second, the ash. I mentioned the ash already. You have to be careful what kind of ash you produce. It cannot be used or is not allowed to be used, depending on your legislation in your country. Then we have the FDG, and here it is maybe problematic the use of your produced gypsum if the biomass changes the quality, and which is maybe outside your legislation or your grounds. And then, of course, we may have some stack emissions. If you talk about sewage sludge with a high amount of mercury. And so that's all not very easy. However, experience so far showed, let's give the reason why we have this in-boiler problems. You see here the ash fusion characteristics of different straw samples in the middle. This wider field gives you an idea of different European straws which have fusion temperatures and softening temperatures which are much lower, as you see this, if you compare the center-right field with the European hard coals on the left side. Also, the second from the left, the wood samples have lower softening and hemispheric points. So that means slagging and fouling is one of the problems which you may run into the high temperature areas of your boilers. We also, you see here on the very right side, the energy crops also have quite low softening temperatures. And that is a typical example of a straw-fired boiler after God knows I don't know how many hours of operation, but this happens very fast. In particular, if this temperature range is the normal bituminous coal-fired range. In fluidized baths, you have the lower temperature. There is obviously not a real problem, or not a real problem, and not such a big problem. Another thing is in this circulating fluidized bed, you see all the caps here, the feeding caps on the bottom. That is brand new, and after a certain time, you have not only some corrosion here on the caps you see here, but you have also some plugging of caps. But by proper research and development, these problems were overcome. But if you run with this kind of fuel the first time, be careful. Also, we do have in this photo here some the little pipes are parts cut out of this boiler here, and you see some slagging on top of the yellow slagging here, or the reddish slagging in different temperature ranges, and then you have the microphotos here from some corrosion of the top areas of the just below, actually below the slagging. So, slowly coming to the end, we do have obstacles for co-utilization. We need detailed data about the fuel supply and the quality, otherwise you may get into trouble. Some of the troubles I might mention. The fuel costs are also mentioned. We have some impact of the new supplemental fuels on the systems, the available systems, and as I mentioned earlier, the use of fly ashes is so far not possible in Europe in cement installation or cement production because of the impact of quality or the legislation you have. Also, the units need extensive permission requirements depending on your country, or the legislation there. And we have also now the liberalization of the electricity market with the problem that the biomass utilization is probably not as interesting for the industry anymore. Still, we know, and that is important, we know that co-utilization in combustion and gasification is positive. You have a co-utilization which is environmentally beneficial, which is technologically feasible if you watch the few lines I mentioned, and it is economically attractive. Still depends how expensive your other fuels are. And if you're further interested, look into the IEA reports. Here are some tables from recent IEA reports, and you see here how many experience there is in Europe. For example, the first table, I can't see it on a small scale here. That is, one table is in Great Britain, the other one is in Germany, and the third one is in Holland. Okay, you see, we had a lot of, in the last 15, 20 years, the last decades, we had a lot of experience done, and if what's the status quo today? There are more than 100 demonstration projects in Europe, and some are still on large scale operating. Major overview reports are available, particularly by the IEA. I mentioned here the most important one is 3 months here, and some books available also. Since you will have the slides available later on, distributed by the organizers here, you can have the reference data here. Improvements on large-scale operating is ongoing, and I will give some more recent experience tomorrow. And for the time being, we are thinking about, we are discussing cooperation with non-European countries, which is, as you know here, that's the reason why we are here. That is with your country, with China, with Indonesia, and others. Projects are ongoing. Thank you very much.